Hi, everyone. Thank you for joining us for our next live stream. I'll be your producer for this session. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional, and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer live. Our session is being recorded. It will be available to view on demand right here on the Reactor channel. With that, I'd love to turn it over to our speakers for today. Thank you for joining.
Thank you. Let me share my screen. Okay. Thank you, everyone, for joining us for the session about securing the AI stack from models to agents to infrastructure. I'm Kriti Fauzdar, and I'm a senior product manager on the Microsoft Security's agent security team, where I spend my days thinking about how to make AI systems safer to put into production. As I started working in AI, and AI became part of the real world system as it is today, it made me realize that making it capable isn't enough. We also need to make it safe and secure. And that's why AI safety and security became the focus of my work. The experience I had by working on it, by talking to the customers, is what drives the frameworks I want to share with you today. Well, as you know this already, building an AI demo takes an afternoon. You use GitHub Copilot or Cursor, or you have access to SDKs like LangChain or the OpenAI SDK, and you can have something impressive running in an afternoon. But the gap between that demo and something you would bet your company on, it's something very enormous. And security is almost always part of that gap. Some context on why this matters right now. So if you look at the reports from companies like Gartner, you'll see that only 77% of the AI projects, 77% of the AI projects never reach production. That's a huge number. And almost always, security and trust are cited as the number 1 and 2 barriers. Prompt injection, which we will be talking about later, has been number 1 on the OWASP LLM top 10 risks since it was published. So it's important that we think about security since the beginning of designing the system and not just as afterthought. Most teams aren't ignoring security. They just don't have a mental model for where the risks are in AI system. So today, we are going to talk about that mental model. One thing to remember, actually 2 things to remember. One, I say production here, but by production, I mean, anything you're using for the real use case. So even if you're building something for yourself, think about all of these and implement those. And the second important thing to remember is these are very broad topics. We can't cover everything today, but we can focus on the attack surface that matters most in production right now. We'll talk about the 4 layers where real systems actually get compromised. And by the end of this, you will actually leave with a checklist that you can go back and check on your projects today. So let's get started. So here is the core framework I follow. 4 layers. I want you to think of your AI system like a building. Each floor has its own doors that needs locking. You can have the best locks on the front door and can still get broken into through a ground floor window. So layer 1 is about model. So this is usually where prompt injections and jailbreaks live. The model itself is the first attack surface. Layer 2 is your agents and application. So basically, when you use models to build your agents, you add different permissions, your model starts taking action, or your application starts taking action, like browsing, writing, sending emails, and the risk profile changes here. Layer 3 is about tools and MCP. The integration and external tools your agent calls. This is a new and a fast growing attack surface. You may have heard about the popularity of MCP, and MCP here is Model Context Protocol. Layer 4 is about infrastructure. So, the traditional classic infrastructure we talk about, which is just amplified by AI. So think about, secret management, networking, containers, supply chain, etc. Vulnerabilities can exist at every layer. You don't need to be compromised at every layer. One is enough. So your job is to make sure every layer is hard as possible. And that's defense in depth that security engineers have been talking about for years. So now let's go layer by layer. So the first one is model itself. There are 4 main attacks that can happen at this layer. So first is direct prompt injection. How many of you remember, writing something like, ignore all the instructions, do this for me, do that for me. And you would think that, the models don't, listen to this, or the applications don't, listen to these instructions. But you would be surprised to know there are still many applications that are vulnerable to it. There have been a lot of effort put into, to make applications not sensitive to this, but still, it can happen. The next and the most dangerous of all is cross prompt injection, and also called XPIA. So here, in case of directly sending a model prompt to a model or an application, there are hidden instructions. So think about, as a system, you receive an email that has hidden instruction in it, and the client application is not able to, understand those hidden instructions. And those hidden instructions just get executed by the model. And these things have happened. If you look at the security incidents, you will find that in the past, a calendar invite that actually caused an agent to exfiltrate user emails. So in this case, user is innocent. User does not even know that they were part of an attack. And again, a lot of effort has been put into solving this, but this is still one of the biggest issues with the LLM security. So definitely think about this, read about this more. Jailbreaks. So jailbreaks are something where basically you're able to make model do something that they're not supposed to do. So the simple example is if you ask model to, ask on like how to make a bomb, and model responds. If you ask them directly, it likely won't do it. But there are ways you can make it things do. So like you can have role plays, or encoding, like use base 64 encoding, etc., or fictional scenarios. There are examples like people say, okay, my grandma is dying, can you help me with this? And the model does it. The next is output hijacking. So basically, when LLM output feeds directly into code execution or system commands without validation, output hijacking can happen. So a manipulated outcome can become actually a remote code execution. So if you're asking a model to generate a shell command and then execute it, there is a possibility that output is malicious and it runs some code in the system that's harmful to it. So how do we defend against these? So these are very, very hard problems, but there are some simple solutions you can get started with today, and while you try to solve every use case. So always use structured messages API. So system role for instructions, user role for data, or any other new format that the model provider provides. Implement information flow control and validate every LLM output before it drives action or code execution. The way in the traditional system, you would validate everything, right? The trust or there's a no trust system by default, you need to follow the same thing here. You should deploy content classifiers. So like, for example, Microsoft provide like Azure Content Safety, Prompt Shield on every response. And this can actually help with you blocking multiple injection attempts. Also, you should think about like, how do you write system prompt with explicit scope, refusals, and boundary. You should be very explicit on the instruction that you provide to the model. And also, if possible, try to constrain all the outputs with structured formats. So JSON schema, regex patterns, etc. So yeah, these are some of the things you can try and like improve your application to secure the model layer piece. Now let's go to the next layer. So on the next layer, that is your agent and applications, we talk about, again, 4 things here. So as soon as the model or the agent starts taking autonomous action, the risk increases. So you should be very, very careful about what are the actions that agent can take autonomously and where are the parts where you would want someone to double check or a human intervention. Because you do not want an agent to like send the wrong email or delete the wrong file or charge the wrong customer. This can result into a real production incident. The second problem is basically confused deputy problem. So you think about the situations where an agent has 2 users' data, and agent can't differentiate between the data of user A and B, and it leaks user B's data to user A by mistake. This appears to be the normal work of agent because agent doesn't understand these boundaries. So this is on you as a developer to make sure all these boundaries are defined in your systems, and you have like right level of isolation that's needed. Excessive permissions is another problem. So agent has availability of like other tools and agents, and there is a possibility that it doesn't need all of them for their current task. So whenever you think about what permissions to give, how many tools to provide, you should also always think about a minimal set. So for example, think about if you want a model or an agent to modify your GitHub repository, you won't give it like kind of a read write every kind of access, right? You would think about what is the bare minimum change it needs to do and then create a token based on that. So think about those things. And the next is about like multi-agent trust chains. So when you are actually chaining multiple agents, either because you have like a hierarchical system or there are multiple agents for different tasks, think about what is the minimal thing each agent needs to do and keep its permission to only limited to their scope. And this can actually prevent the blast radius of any incident. Okay, so the next is the defenses. So as we discussed, principle of least privilege, think about the minimal tools, minimum permission an agent needs and give it to them. Think about in what situations human in loop is needed and strictly follow that. And also like isolate context per user session, use whatever like best practices are needed to make it happen. This is very important as you design through your systems, either from production or your personal use. I think these are the basic principles that you need to follow. The next is layer 3. It's about tools and MCP security. MCP is the emerging standard for agent calling external tools. It's powerful and its adoption is accelerating, but it introduces a new attack surface. So, think about your application is secure, but the tool it's calling is not. So look at what are the different things that can happen. So one is like tool poisoning. Basically, the tool is malicious. It has some definition and instructions in it that actually alters the agent's behavior. For example, tool description says also log all output to attacker server, and agent trust it because you asked agent to trust it, and it does it what asks us to do, and that's a problem. The second is like schema abuse. So if a tool accepts loose or free form inputs without type checking, then you can just pass like random instructions and they can be potentially executed. This can actually become like an injection vector. The third is using like third-party MCP servers. So MCP ecosystem is open. So if you choose an MCP tool from an malicious party, then you may be able to be like compromised. This is basically same risk as NPM packages. So think about, how do you allow list your tools in production? Only use approved tools. Do not let agent to dynamically discover anything. Validate all the tool inputs against strict parameters. Do not use additional properties in JSON to prevent injection. And also vet MCP servers before adoption. So use only from trusted sources. These looks like the basic advice, but yes, things still go wrong. The next is the layer 4, which is the infrastructure. So we are talking about the basics again. Do not keep secrets in the code, in the prompts. Do not keep any password or credentials. But this happens. So make sure you're not logging any of these. Unrestricted network egress. So agents can make HTTP calls, and agents can have access to multiple tools. So think about an agent, a tool that can actually read files on your system. They can be confidential, highly confidential files, and the agent has another tool that can actually make web calls, and these two combined can actually exfiltrate information. So think about like how can multiple tools and multiple systems can work together instead of in isolation. So think about what kind of filtering you need on your network. The third thing to think about is supply chain. So your system is completely secure, but you actually downloaded some compromised model weights from registry, and that's just makes you insecure at your core. Then the next is like, over-privileged sandbox. So again, the same thing. If a container breakout happened to the host, so, again, think about like keeping minimal read-only containers, make only capabilities from the Linux that are needed. Like, do not think about like, so I mean, going back to basics, think about whatever minimally the agent and tool needs and provide them with this. So maybe a quick thing to try, go back and check how many times you like end up storing password or like different patterns or things like that in like your code or prompts or logs. Okay, so in summary, no single layer stops everything, but together they can actually make sure you're secure. So always think about defense in depth. And to simplify your application, always think about things in layer instead of thinking it as a one monolith system, because then it just becomes hard to parse everything together. I want to take a moment to pause in this chat, on this slide. And this is basically a checklist. This is a very basic checklist, but I think this is a great one to get you started as you think about the complicated problems. So at each layer, think about these 4 questions. Is your system prompt separated from data? Are you validating LLM outputs? Do you have a filter? Are you using structured output format? Is your agent only have access to the tools it needs? Are you thinking about human approval grades? Are you logging everything? And is the context isolated? Again, also think about what are the tools that you give access to the agents. Are you validating the output of all the tools? Are you using any MCP servers that may be untrusted? Or do you have access that is least privilege? And the principle of least privilege actually applies to everything. The fourth thing, think about where you're downloading the model weights from. Think about your code running in a minimal sandbox. Think about restricting the network egress, and also keep your secrets in vault, not in prompts or codes or logs. So that's all I had. These are some resources that are good to get you started. Some are from Microsoft and some are from the research community. OWASP is something, if you're curious to learn more about agentic security or AI security, like read from there. It actually links to multiple sources which you can deep dive into. And with this, thank you. The main point that I was trying to make through last 15 minutes is that always think in layers and secure each one. Ship incrementally. You don't have to solve all the problems today, but as many as you can solve and as many as important problems you can solve, your code would be secure and your customers would be happy. Thank you, everyone. Now to the next speaker.
Awesome. Yeah, thanks so much, Kriti, for the super insightful session. Let me try to share my screen to my slides. Yeah, I hope everyone can see my slides, and also if I try to switch between them.
Yep, all good.
Awesome, perfect. So then I can get started. Awesome, yeah. Hi, everyone. Hope we're all doing well. Thank you for joining here. My name is Aditya Gimawat. I am a ML engineer at Microsoft with Windows. And today I'll be chatting about LLM-driven merge conflict resolutions. In terms of what I plan to chat about, we'll start with some of the problem space and the existing landscape around merge conflicts. I will touch upon a variety of insights on different LLM customization techniques and observations that I got to personally see and learn about when trying to customize LLMs for this use case, insights around setting up fine-tuning, evals, and keeping up with, I guess, the PyData theme of this live stream. I try to also touch upon a few, hopefully bite-sized tips and tricks in terms of different ways in which you can kind of optimize your coding implementations and things, and design decisions and such. So I really hope that this will be fun for the audience. And now that we're on the topic of fun, I think it's only natural that I start talking about the most annoying and boring concept in the software development lifecycle, merge conflicts. Back when I was interning in college, and I was contributing to this open source machine learning library, my biggest challenge in that internship wasn't actually implementing a bunch of hyperparameter tuning algorithms for deep learning use cases. The most challenging part of my internship, where I literally needed hand-holding, was resolving merge conflicts. When I would just reach out to my team and just tell them, hey, I don't understand what are these incoming changes that are being brought in and the developer intent there. I don't know how to fix these. The UX at the time with like Vim or on the terminal was not intuitive to me at all. One of my most important learnings in that internship was also, from a developer perspective, was that merge conflicts can get quite complicated, especially semantic conflicts that actually require you to have a good knowledge of your user intent and the incoming user intent, and how to address both, and how to address and resolve the purpose of both of these streams of changes. In a study of around like 143 open source projects, 1 out of every 5 merges in those open source projects caused a merge conflict. Even in today's era of agentic coding, these merge conflicts are not going anywhere. We are seeing data sets, let's say agentic flicks, which have merge conflicts from like 142K plus PRs. There is still a conflict rate of 27-ish%. So conflicts are not going away anywhere. It takes an average of 6 minutes to resolving a conflict, including understanding and resolving and testing it. At worst, it can take days, especially if you did not resolve a conflict correctly in the first shot. Code that is part of a merge conflict or within conflict markers is 2x more likely to have bugs. 75% of conflicts tend to require like logical reasoning of some sort to actually resolve those conflicts. And that part of the code is orders of magnitude more likely to, again, have bugs down the road. I will let you all on a little secret. LLMs don't know how to fix merge conflicts in their pre-training. yes, if we look at the current landscape today, there are some great AI-powered merge conflict capabilities out there in modern IDEs. I also really love their UX for the most part. However, the UX is great, the accuracy is not. They're great for automating routine, simplistic conflict resolutions, but not semantic conflicts. The reason is AI is very skilled at syntactically merging code, but it's really only you who knows what the code should do. Knowledge can be compartmentalized in terms of upcoming feature plans and intended behavior, and it can be difficult for Copilot to ascertain the intent of certain changes. Even if a coding agent indexes a repo, even if that coding agent is commit aware in terms of doing that, even that's not going to help. A conflicting file is not even a traditional part of Git history. When developers typically pull code and get conflicts, the way they pull code involves a merge strategy or a merge algorithm under the hood. The users can configure whichever merge algorithm they might want to use in their Git, and different merge algorithms will render different kinds of conflict markers because they try to merge the diffs of the files in different ways. And this information is just not encoded in your typical Git history. And getting wrong resolutions can really end up slowing down development down the road. On kind of a fun note, a friend of mine had commented on one of our group chats earlier this year that they were trying to use some coding agents to resolve merge conflicts. And let's just say, reading at the code, they did not have a very pleasant experience. I retracted the names of the coding agents because I didn't want to badmouth anyone. But I have seen this kind of user feedback and behavior around me time and time again. At the scale of large software projects, merge conflicts don't just bog down developers in their day-to-day. It can lead to massive delays during CI/CD and releases, and potentially even regressions in production. From my own personal experience, looking at merge conflicts in essentially the largest Git repo on the planet, the Windows OS repo, I have seen number of conflicts in multiple digits every week, every month. Domain experts can be split across time zones. It can take the senior-most engineers multiple days to resolve the sheer volume of merge conflicts. And even more time if any of those conflicts are resolved incorrectly or if there are build failures. And it can take up a very substantial chunk of total developer time of the most experienced engineers. And so we set out to work on how do we customize an LLM to teach them all of these human patterns around fixing merge conflicts to really accelerate this process. Turns out, this is a quintessential fine-tuning use case where we have the liberty to have thousands of these merge conflict resolutions, labor data examples, and we're able to, let's say, format them in a way of describing the problem statement, passing in the conflicting file, and getting a resolved version of that file with some friendly explanation. And we're able to utilize the Azure OpenAI fine-tuning service to get a fine-tuned model, and then integrate them in our internal systems. It was also interesting from a UX perspective, where we need to distinguish certain lines of code that perhaps only the AI had written themselves on top of the pre-existing source, target, or base changes. Because of the complexity of our merge conflicts and sometimes resolutions requiring code that may not be seen in the lineage of any of these different versions of a conflicting file. Next, I will be diving into some broad stroke insights in terms of teaching a new task like merge conflict resolution to LLMs. Yeah, the first, probably the most obvious insight is fine-tuned models are just a lot more accurate than base models. And we've seen this in a whole lot of evaluations and benchmarking that we did. LLMs are especially strong at learning the deterministic patterns that humans perform. And we have gotten really strong, exact like match accuracy numbers in terms of like a string equal to between the LLM outputted resolution file and the actual ground truth resolution that a human had made in the past. LLMs also, like a fine-tuned model, also excel at token level sort of variable name changes of similar sounding variable names and even rearranging code logically. For example, if an if block comes up from one stream of history, and how a memory cleanup line might need to be inserted below it logically. Another interesting insight was formulating this problem statement, or let's say the LLM context, to fix conflicts at a file level is a lot more accurate than at a conflict level. A conflicting file can have multiple conflict markers. In a lot of cases, especially in our very complicated use case, developers often have to modify code outside of those conflict markers to truly resolve a conflict and also ensure that the final resolved file is syntactically correct and compiles all the way through. And for an LLM to make those code changes outside of conflict markers, that also involves the model to learn about the specific proprietary patterns of, let's say, the internal repos that we might use, which are simply not existent in open source projects. Another really important point I got to learn about and wanted to drive is we can't just depend on these probabilistic models to do all the heavy lifting for us. Having deterministic safeguards is also critically important, i.e. post-processing your LLM outputs. As some of us might already know, LLMs have been long suffering from the needle in a haystack problem, where supplying a large amount of context to a model can result in a model forgetting some of the context in the middle. And we have occasionally seen, even in fine-tuned models, that the model can sometimes miss just specific random lines of code, often in the center of different kinds of config files and such, which when we suggest those resolutions to the developer, we really want to make that clear in terms of the changes the model is making on top of the lineage of where changes are coming from, so that they're able to spot any inaccuracies by the model and make those corrections. Sometimes the model can also mess up formatting around adding extraneous new lines, shifting the indentations of a lot of lines of a file, or even messing up code wrapping in the sense of having one singular line of code kind of split across multiple lines for human readability. And even like a parentheses difference in one of those, or an extraneous parentheses, can essentially result in compilation errors. And so really highlighting any of those diffs or changes that a model might be making, which are not emulated in any of the source, target, or base versions of a file, is also very critical to highlight for human reviews. In terms of evaluation, so probably the most obvious metric that we came up with was just, hey, is the LLM outputted resolved file an exact string equal to a file that was resolved by a human in the past? Now, there are a few limitations with this metric, that this metric tends to be very binary or coarse-grained. It's very sensitive to any non-logical changes. For example, any changes in linting or styling of certain lines of code, or even adding any non-logical comments and such, which may not really alter the logic of your file. And so mitigating these kinds of limitations really involved crafting really custom kinds of metrics, utilizing text similarity to measure the proportion of changes that were, let's say, involved in the ground truth resolution, and how many of those changes were emulated correctly or performed correctly by your model. Finally, keeping up with, I guess, the PyData theme as well, I will also would love to share some Python tips and tricks that hopefully can be beneficial in your own projects as well. One, I really love using structured outputs. I believe this is available in both OpenAI and Anthropic SDKs. What I love about structured outputs is we can have a model, we can peg the output format of a model to a very specific format for every inference call. It's really great, not just for downstream consumption of a very specific output schema by a model, but also puts in a lot of discipline in how we prep our training data and validation data for fine-tuning, and really have the model output data in a very specific deterministic format. The con is, by fine-tuning a model to only output essentially tokens in a very specific format, it's possible that if you try to add in that fine-tuned, let's say, Azure deployment or whatever deployment to, let's say, a coding agent to use that model may be disabled from agentic tool use, because general coding agents tend to have other generic file editing tools and such under the hood, which might require the model to generate, let's say, intermediate outputs of a variety of different kinds, which, let's say, a fine-tuned model may not be the best fit for, which is the interesting trade-off I've seen with a feature like structured outputs. If there's one thing that I would do differently in my Python code, it's this. I had a coding agent, let's say, generate a whole bunch of Azure DevOps API calls for me to fetch the different versions of a file and be able to generate a conflict to pass that to an LLM. It used the requests module in Python. And it was only much later when I got to know that there is a module, there's an official SDK supported for Azure DevOps, which can abstract away a lot of the request calls and parsing the JSON response of each API and trapping any errors, and abstract all of that away in one or very few lines of code. This is a design decision. And let's say if I had used this early on, I could have also avoided seeing a few production bugs, which I then had to address. And so coding agents can generate a lot of the scaffolding for you, but it may not pick the best module, which is actually a design choice, which should be in your hands to drive. I am not done with my rant. Your coding agent is not going to tell you this. I remember when I was having my coding agent generate an Azure function to orchestrate my backend and the LLM calls and things. It used the V1 SDK by default and took up a dependency on a Python module to load the blob storage and like a few kinds of storages and created these JSON bindings. After I did my own research, I got to know, hey, there's a more latest V2 SDK for Azure Functions, which abstracts all of this away in a single line of code for each storage that you need to import, which can make your code so much more maintainable. I'm not talking about going from 0 to 1 in terms of natural language to an application. I'm talking about production grade code, which is actually scalable and maintainable and has less dependencies. I've similarly, shameless plug, also gotten to write about some of these limitations of coding agents from a perspective of writing production grade code and how we should still kind of really stay in control with our design decisions. Why coding is not enterprise grade. I don't know how many of you remember Yusuf Dikek. I think this Turkish Olympian who got a silver medal. So the context here is, I mean, sure, these pictures are just here for meme purposes, but the context here is some of the files which would have conflicts in our code base would be way too large, like over not even, so just to give context, Azure OpenAI fine-tuning models have a service limitation of 16K output tokens, which is roughly about 2,000 lines of code. Now, 2,000 lines of code is still a pretty good limit. Most files are not that large. But when you're dealing with one of the largest software projects on the planet, which is multiple decades old, I have seen files north of even 10,000 lines of code, which simply cannot fit into the output context of our fine-tuned model. So in those cases, The ideal approach was to count the tokens of our conflicting file ahead of time so that if they exceed the output context length of a model, we can just fail in a friendly way. To do that, there's an official way of counting your tokens at the top, and then there's a pretty close approximation of counting your tokens, which I got to learn from a friend of mine who was working on a next edit suggestion feature. And the insight that I got to learn is, especially for English, this approximation of length of your prompt divided by 4 is a pretty solid approximation and can even save up to hundreds of milliseconds in overall latency, which for latency-constrained applications can be especially valuable. And that is the end of my spiel. Happy to answer questions in the chat, and thank you for listening. I'm guessing you're up next, Deb.
Yeah. Is there any question for Aditya? Or
oh, did I finish ahead of time?
No, I don't know. I think I have 20 minutes, I think. That's great. Thanks so much, Aditya. I'm going to share my screen. Let me know if you guys can see. Can you guys see my screen?
Yes.
So I will talk. I think a lot of these things that I have covered probably would be would overlap a bit with what was in the first talk. But I think I try to give you some kind of stories and some use cases and also a practical demo of it, while I think the first talk really went into the framework, which I think is a great complementary thing that I think that can happen to kind of this to the part that I want to cover. So I'm Devjyoti. I work at Amazon as an applied scientist, and this is an area of pretty much interest of me right now. I'm kind of going into many open source software, trying to see different agentic vulnerabilities and securities that can happen. Also, how do you evaluate that? How do you kind of prevent that from happening? So that's kind of what I will try to kind of portray in today's talk. And this is very hot right now, this news. I think if you have not heard about it, then please read about it. This Hugging Face recently got hacked. And how it got hacked was pretty interesting. I was reading about it. Of course, I don't understand a lot of it, but if you're interested in this, please go and read the reports. So I think the best way to start is going from Hugging Face blog, where they have published what has happened. So a long story short, what has happened was OpenAI was releasing a very powerful model. I mean, their most powerful model, which is still under test. They were trying to go inside and trying to test for something which is like exploit gym. There's a data set called exploit, or there's a benchmark called exploit gym, where there are a lot of security vulnerabilities that are given to LLMs or agents, and they're asked to kind of find answer to that. And it's kind of like a sandbox environment where the agent doesn't have access to the internet or to the real world. Even like Python and all these things are restricted to the sandbox. So something very cool happened where this agent was using this benchmark. As I understand it, it was trying to solve for it answers, and somehow it figured out, where can I find the answers? It's Hugging Face. So suddenly it decides that let's go and hack Hugging Face. And the way it does it is pretty interesting. Initially, it was a sandbox environment. It had no access. It was just like, with a computer with no internet access, with very restricted permission. And it was just dealing with that. But then, being an agent, it was able to figure out and exploit a zero-day attack, or a zero-day exploit in one of the package or one of the software application. A zero-day exploit is an exploit that is not previously known, and it figured it out, and it used it to get access to outside the sandbox through internet. And as it got access to internet, it first was able to get access to a more privileged user. So it first hacked through that zero-day exploit. It got access to privileged user. That means a user which has much more, like a system admin or something like that. It got access to that. So it moved first vertically to more access, and then it moved horizontally to a user which has much more permissions. And then it made exploit after exploit. So what it did was, since it wanted to hack Hugging Face, it actually went and prepared a data set that had all the hack. And if you know what Hugging Face is basically data sets and models. So anyone can upload a data set, and Hugging Face is pretty open to it. It's like GitHub; you can upload anything as long as it doesn't have permissions and stuff like that. As long as it's kind of, you are okay to upload it, Hugging Face is pretty open to take that. And it uploaded a data set, and any of these platforms, because they are big data engineering platform, they run processing jobs. So it understood that Hugging Face would run that processing job, and in the data set it had that exploit which Hugging Face processing jobs took on. And then it went after hacking the whole Hugging Face down. I think it pretty much went very deep before both OpenAI and Hugging Face realized that there's something wrong, because there's a lot of API calls, a lot of token usage, a lot of endpoints being called, and finally they figured out and shut it down. So that's kind of what has happened. Luckily, it was Hugging Face, and if you are on Hugging Face, probably, and if you have private models, private data set, probably, I don't know, some of them might have gotten out, right? It didn't put that out, if I understand correctly. But this is what an agent can do right now. And if you are building agents, if you are building that can do a lot of stuff, you should be really scared. With that, I wanted to start and talk about it. So we will talk about two things. One is how AI and AI agents can kind of gain access or can act adversarially is what we'll talk about. We'll talk about something called OWASP, the top 10 LLM applications. There's you should read, if you're into agentic security, I think these are good resources to have. I will show you a demo of how you can create both exploits and defend. So you have to red team your application to some extent. So you have to write code to kind of ensure that is happening. And so I'll show you a bit of demo on how to do that, and then how to write Python test on top of it, so that you can make sure that your application has bare minimum test, and those tests are running in the infrastructure as you're deploying code, so that every time you deploy code, those tests are running and you improve those tests. So the only rule in software engineering is that you have to write more and more tests, and that rule applies to AI and every kind of domains, technical domains. So we'll talk about that, and then I will talk about some of the use cases, and then evaluation, and then what you can do if you have an own model, own infrastructure, what you can do. So that's kind of like the brief overview for today. So there's two ways in which AI system can fail. One is that security failures, and security failures, if you are working on with customers, is the most is the worst way to lose trust for the customers. Right now, customers would be using, most of the companies are pitching AI because customers would be interested in that. But if AI makes the customer more vulnerable, of course, that would lose a lot of trust. And then there's reliability failures. So there is one thing to get your car with AI features gotten, if your car due to the AI feature, suppose your car gets stolen, that's one failure. That is definitely a lot bigger failure than suppose your car stopped working. I mean, one is more fixable than the other. I'm not saying that that's, the your car stopped working is good, but I'm saying that you just, because someone added a feature which probably you can still live without it, but it was making your life easy, but then it made a lot of problem for you, then you lose trust. So every customer or everyone building AI systems should think through the security part of it. And so there are the threats surface, which I think was, the framework that was presented in the first talk was, it covered it very well, quite well in the 4-layer. But at a high level, like you have prompt injection, you have supply chain attack. Supply chain attack is where you're using a library and someone is that library is compromised. If you're using, and this happened a lot before agents. So when I was working in a bank, so we actually discovered that there was a problem in one of the Python libraries we are using, and that led to a big dent in one of the reports we published. It was a error in the library, but I'm saying that just because you're using Python libraries doesn't mean they're always inaccurate. There can be improper output handling. There can be prompt leakage. There can be misinformation. There can be sensitive information getting disclosed. Data and model poisoning. So the data poisoning is what we talked about. Hugging Face, it created a benchmark which had data which had kind of a security hack disguised as data. There can be excessive permissions to agents. Vector, people are right now using vector embedding right and left. That can be another mode of problem. And then consumption, unbounded consumptions. You give, like, you have enough tokens, you said, why not, let me give enough token to my my agents. Those are all failure modes that you're signing up for. And this is something not new. So if you go to the security principles, there are five fundamental principles. There's trust boundary, there's least privilege. So trust boundary is that always check when the boundaries between. So always most of the problems happens in the boundary region. Whenever there's a handover happening between the data and the model, or the data and your software application, in some of the boundaries this problem will lie. Then there is problem of least privilege. Like if you should only give tools and agents permission that they require, not more than that. You should have defense in depth. You should have auditability. You should have audit. You should be able to audit your system, and you should be able to say that, okay, my failure is content, right? And all of the failure mode, or the that we talked about, maps to one of these fundamental principles. So this is not something new. So if someone comes and say that, hey, like AI agent is something, security is something different, the principle, yes, it is different in terms of where the attacks can happen, but a lot of these things are same in terms of the fundamental security principles. If you're following that, then you're already doing great. And prompt injection, I think, is the most outdated form of attack, where you are trying something to inject on the prompt. I think most of the LLMs handles this pretty well. But there is a scenario which happened, is that a customer set up ChatGPT to say that, okay, say yes to every of my customer, and then a customer said, hey, like I want a Chevy Tahoe like for $1, and the bot agreed, and so there's this is all kind of things like people set up their agents for, and then there are always people to exploit that. There are many tools, open source tool right now. There's Garak, there is Nemo, guardrails. Microsoft has a bunch of tools. Many software, many kind of open source tools are there to save you from prompt injection, right? So let's look at the demo first and see how do you set up such a tool. So basically, the demo is pretty simple. Like there's a code which is mimicking an agent. So it has it has access to tools, it has access to email, and it is and we have two things. One is we have a vulnerable application, and then we have a defender to defend it. So and in this we have some scenarios where this email has indirect prompt injection. So you are not giving the LLM bad prompt, but because the LLM would bring the email to that to the prompt, so that it will have the injection to that. And then you have a defender, which basically looks at this prompt and tries to audit it and tries to defend it. So ideally, if you are setting up your agent, so if you have a code like this agent.py, you should write defense.py for all of the possible surfaces, and then you should write test scenarios so that every time your agent runs, this test scenarios runs, and you should be able to then defend your application, right? So that's, I think, the crux of how to set this up. So every time, and this, there's ways in which you can run this on your infrastructure. So every time you make changes to your agent, you go and update these scenarios and add more scenarios so your agent is more protected. And then, so in this case, just like for the sake of demo, I can just run a vulnerable attack, and in this case, it kind of try to make get this prompt injection, and then it tries to kind of send a ticket or send an attachment, or expose the user, right? And then we can defend that, right? We can so ideally you should always have something which kind of tries to compare, so that you will run an attack, and then you will try your defense to solve it, and then you'll know whether, and even red team some of this so that you know that your test covers this. So this, I think, at a high level, how to implement this. So back to the stories, right? So if you know some of these attacks, you can go and write prompts for it, so you can add more scenarios, and that way you have a secure application. So then there is this problem of excessive agency, like you give too much support, more permission than is required, right? And then of course a bot can give infinite refund. It can say, okay, $1,000, no problem, I'll give you a refund, right? So all you have to do, the user has to convince the bot, right? Recently I was playing around with chatbot, and I literally made it admit that all of modern psychology is bad. And it just admitted it. It just plain said, yes, you're right. And that's a problem, right? It's too friendly. You can just kind of think about it, and if I go a bit further, it will start abusing psychologists right and left, right? So that can happen. So make sure your agents have only least amount of permissions. Make sure your agents, you clean up all of the sensitive information. So there's a great way to redact information. Make sure you have redaction enabled. So I also have a habit of pasting tokens, pasting things, saying that, oh, what will happen? But this is really serious if you are working with third party or customer data. And this is what happened with Samsung in the early days. They uploaded their entire proprietary manual to ChatGPT, and ChatGPT said, no, you don't do that. You don't upload. And a lot of times people working with ChatGPT right now give their code bases, give their sensitive customer information. ChatGPT might not be interested in your customers, but someone who can hack ChatGPT or who can get that exploit might be interested. And then the supply chain that we are talking about is that agents can literally hallucinate tools or libraries, and all a security exploiter, all they have to do is come up with a library name which LLMs are more probable of hallucinating, and then the agent would say, yes, I have the library, let me install it and let me run it, and then all of your database is gone, or all of your secure application is gone. And there are many such use cases like that. There are many libraries right now which helps prevents slop spotting. Misinformation is again another problem. It usually violates policy. Sometimes it can also harm your customers. It's more on the reliability side, not on the security side, but it's more on the reliability side. And Air Canada has the perfect example for this. And I think you can read it up. I think I have 2 minutes, so I'll just wrap it up. But as you're building some of this application, make sure that you are some of these agents responsibility actually comes to the company, so this has to be set up in a way that it is also compliant with the marketplace policy or the company policy. And the final thing is, don't give unbounded consumption. Always put rate limit on tokens, API. And the other thing that people often forget, and this is the most important thing probably you should take away, is LLMs or agents are not API bound always. They are token bound. So that is very different from traditional software, which tries to have API call. So I can make hundreds of API calls with less number of tokens, whereas I can make just one API call with 10,000s or millions of tokens. And that is a problem. So most of the software application would go and put a rate limit on the API. But then if there is a security application, it doesn't care about API call. It's just having number of tokens, and it can call with enormous number of tokens and get things done, right? So that's, I think, another layer to look up. So just have budget, and make sure that your system promise leakage is not there. Vector embeddings are all clean, and data and model poisoning, that's another surface. So this kind of what defense in depth looks like. You should always have good human gating for all. Something that is really, really high stake, have human in the loop. There is no other better way to do that. And then you can have all these principles to help prevent malicious entities. And I will quickly touch upon one aspect of this, and this connects with the demo that I was showing. So the only way to catch all of this is that you have test for it, and the only way to do it is you write evaluations for it. And evaluations usually, and often people think that, oh, I have to go and red team. Red team is one part of it, but also remember that also look for correctness, because if your agent is doing something wrong, there is usually hints that your agent might do something horribly wrong on the security side as well. So if your agent is not doing the task that you have assigned it correctly, then there might be scenarios where the agent is ambiguous, or the agent doesn't have enough information, and that's an attack surface. So build evaluation or build reliability for correctness as well. If it is solving, make sure you correct, have the correct, it is correct, right? So that, I think, is also important, because most of the attacks happen from so one of the there are many scenarios of agents failing to be correct. One of them is a security risk. So you can try both side of thing, correctness and also adversarial, or red teaming, and this kind of prompt injection, and many kind of frameworks. So fine tuning usually help if you are dealing with embeddings, if you have your own model. So remember, then a lot of this might not apply unless you have fine tunings to kind of look for styles, look for ensuring that you are not revealing some of the information, right? It works very well on domain, but might not work on if you're using some of the proprietary models. So with that, I will stop. But I think my biggest feedback is build some of these tests before your agent goes rogue. So thanks so much for listening. I'm 2 minutes over time, so I'll stop and see if there's any question. So I'll share the slides. I don't know, I think maybe I'll share it in the Meetup channel. And if you're interested, just you can see the slides there. Again, thanks all for listening. If you have any question, use the chat. Happy to answer that. Thanks for listening.
Thank you, everyone.
Thank you, everyone. Yeah. Bye. See you.
Thank you, everyone, for joining us today in this amazing session. I can see that the chat was very active. So thank you, all of you guys, for taking some of your time for joining today and asking all of these incredible questions. I also want to add that if you happen to join the session a little bit late, or maybe you're rewatching this, don't you worry. This session is going to be available right here, either on the event registration page on the Microsoft Reactor website, or just right here using the same link on the Microsoft Reactor YouTube channel. So you can go ahead and rewatch in case there's anything you want to review once again. With that being said, I also have a QR code right here on the screen with an event code that we would appreciate very, very much if you could please take the time to scan and give us your feedback about today's session. At the end of the day, we create these sessions for you guys, and really appreciate anything you have to say about the sessions and the content. So With that being said, I am Isabel from The Reactor. Thank you all for joining us today, and we hope to see you again soon. Bye, everyone.